Hey everyone, in this video, I'll go over a motor simulator software I made. To begin with, let's look at a simple electric circuit. We have a voltage source and a resistor. This circuit represents one motor phase, and according to Ohm's law, we know exactly what voltage we need to get the desired current. So let's see what's the current response to a voltage step command based on this model. Okay, that was an immediate response, and the relation between the current and the voltage is defined by the resistance. Great. This doesn't make much sense though. Now, does it? How could the response be immediate? It doesn't seem physical. This is because when talking about motors, the so-called resistor is actually a wire that's coiled around some metal, which is essentially an inductor. So let's change the model of our motor phase to a resistor in series with an inductor. An inductor's resistance, or more accurately its impedance, is frequency dependent. The higher the frequency, the higher the impedance. Let's see the current response to the same voltage command. Okay, this makes much more sense, right? The current changes gradually and still converges to the same value, since the frequency is 0 after the initial step, and the inductor doesn't add any resistance at 0 frequency. Now, the model we used was simplified. In actuality, the phase voltage is a combination of Ohm's law, so V equals I times R, and Faraday's law, which says that the voltage induced on a coil is the change in flux linkage. The flux linkage is pretty much the magnetic field passing through a coil. So V equals I times R plus d lambda dt. You might be wondering, where's the inductance I talked about earlier? Well, it's part of the flux linkage. As we know, passing current through a coil generates a magnetic field through the coil. So we can model the flux linkage passing through the coil as the inductance multiplied by the current. Lambda equals L times I. But for permanent magnet motors, there is another part that contributes to the flux linkage, and that's the magnetic field generated by the permanent magnets. So lambda equals L times I plus psi. So that's the flux linkage. But for Faraday's law, we need the time derivative of the flux linkage. Okay, so what in lambda is time dependent? The current can definitely change with time. In motor control, we usually command sinusoidal current waveforms. The inductance can also change with time, since the inductance is position dependent and isn't necessarily constant as the motor spins. There are some motors that specifically work based on the difference in inductance to generate torque, such as reluctance motors. And the flux resulting from the permanent magnets also changes with time, since it's also position dependent. We can see here that the permanent magnets are inserted with alternating polarities, and so the flux changes in the same manner. The shape of the flux depends on the motor construction and the shape of the permanent magnets. In this simulation, I assume a sinusoidal flux from the permanent magnets with the option of adding harmonics. So what we're left with is the following equation. And since the inductance and permanent magnet flux are both position dependent rather than time dependent, we get the following. That's because the time derivative of the angle is simply the speed. And that's how we get the phase voltage equation, where d lambda d theta is the back EMF constant. Now, we only talked about a single phase thus far. When taking into consideration three-phase motors, we also have mutual inductance, where the magnetic field generated by any of the phases passes through the other phases, or in essence, their flux is linked to the other phases. So after taking into account three-phase motors, we get the following. Alright, now that we have the three-phase equations, before we try to solve them, how do they affect or constrain each other? We always care about the voltage differences between the phases, since that's what defines the resulting currents. So we need to add some constraints to define how each of the phase voltages affect each other. Let's assume a Y configuration. According to Kirchhoff's current law, the sum of the currents coming in and out of the middle node is 0. Additionally, the actual phase voltages are determined by the difference between two voltages, the voltage commanded by the inverter and the neutral voltage, which is the voltage in the middle node. The voltage commanded by the inverter is known since we're going to command it. And the neutral voltage we have to solve for. In a balanced system, where all the phases are identical, we could simply assume that the voltage at the neutral point is zero, since the neutral voltage is the sum of the three phase voltages, and the sum of three identical sine waves shifted by 120 degrees is zero. However, there are always some slight differences between the phases, like a different inductance or resistance, so solving for this neutral voltage will allow the simulation to handle variations between the phases, and thus give a more general solution. So now, we need to update the phase voltage equations by adding the neutral voltage. And finally, what we actually want to find are the phase currents. To do that, we'll solve the differential equations of the current derivatives, so we need to reorganize the equations a bit. Now, let's change it to matrix form to solve it more easily using a numerical library. And in this format, we can solve a set of linear equations, ax equals b. Now, let's look how this part was implemented in the code. We can see the A matrix, which is the inductance matrix, with a row and a column of ones concatenated to the end. The row of ones will be used to ensure Kirchhoff's current law. Now, a small issue here is that this row ensures that the sum of the current derivatives will be zero, while Kirchhoff's current law requires the sum of the currents themselves to be zero, not the sum of their derivatives. And since I'm solving for the current derivatives, I need to add another constraint to handle this discrepancy. This additional constraint is to initialize the currents to zero at the beginning of the simulation. This will ensure Kirchhoff's current law is satisfied initially, and since the sum of the current derivatives is zero, this law will continue to be satisfied throughout the simulation. Okay, that's regarding the row of ones. The column of ones will be used to take the neutral voltage into account as well. Moving on to the vector b. This vector contains the voltage equations as well as a concatenated zero. This zero is also part of ensuring Kirchhoff's current law is satisfied. X is the current time derivative vector with the neutral voltage concatenated to the end. Next up, we solve the linear equations. This final column is what adds the neutral voltage to the phase equations. And this final row is what adds the sum of the derivatives equal to zero equation to ensure Kirchhoff's current law. We solve these equations every simulation cycle, which are very short periods of time. Short enough to capture the actual physics, but not too short so that the simulation takes forever to run. Okay, now that we solved for the phase currents, that's pretty much the end of the simulation cycle. And although it's probably the main part, there are a lot of parts that led us up to it. So how do we get to this point? Well, as Simon Bloxford often said, when things are obscure, a block diagram's the cure. Let's look at a simplified block diagram that explains what the simulation contains. Okay, so in addition to the simulated motor, I also wanted to simulate the control side. So we have a controller, which is the brains of the operation. Based on the desired commands, it runs all the calculations and gets the phase currents, which we find through solving differential equations. By the way, there's no position sensor right now since the speed and angle are calculated by the simulation. The controller commands the inverter, which is the part that actually sets the voltage on the phase terminals. Now let's look at a slightly more detailed block diagram to explain all the parts entailed in this simulation before diving into each block. First of all, we have the commands, which are the speed and the current vector. Next up, we need to find the sensed D and Q axis currents, since we need to know where we are compared to the commands. Now that we have the commanded current and the sensed current, we'll use these values to generate an error, which the PI controller will gladly gobble up and in return spit out the D and Q axis voltages required to minimize the errors. Next up, we need to take these voltage commands and transform them into PWM commands. These PWM commands must also take dead time into account. Now, before we start solving for the phase currents, we need to update some additional parameters, some of which we'll use to solve those equations. The rotor angle, the inductances, the back EMF, and the resulting torque. And finally, we get to where we started, calculating the phase currents based on the previous phase currents and the commanded voltages. Alright, let's go over the separate blocks now. Starting with the ramped commands. Both the current vector and the speed change based on a ramp. Every cycle, the value updates based on the previous command and the ramp size multiplied by the time step. The speed can change in two different methods. The first one is allowing the user to simply set the desired speed and acceleration, as if there's an external motor under speed control running the tested motor, like a dynamometer. The second method is based on motor dynamics. The torque generated by the motor, as well as its inertia and friction, define its acceleration and subsequently its speed. The current vector changes based on the defined ramps. We'll be using field-oriented control, which means we'll look at the current vector's projections on the direct and quadrature axes, so the D and Q axis currents. That way, we'll have two DC currents to control instead of three AC currents, which is more cumbersome. This also allows for controlling the D axis directly, allowing for easier use of the field weakening technique. Next up is getting the sensed Q and D currents. We'll find them by taking the phase currents from the previous simulation cycle and transforming them into the D and Q axes. We'll use the direct transforms, which are a combination of the Clark and Park transforms. Next, we feed the errors to the PI controllers. I'll run the PI controller every sampling time. The default sampling time in this simulation is 62.5 microseconds, which is a sampling frequency of 16 kHz. This PI controller is in a parallel configuration, so the integral and proportional parts act on the error independently, then they're summed together. There is also a voltage limiter, so if the amplitude exceeds the maximum voltage amplitude, the integral is clamped up so it doesn't integrate anymore, and the voltage outputs are limited as well. After getting the D and Q axis voltages, we need to transform them into the ABC frame of reference, since we command our power module in that frame of reference. Next up, we add a third harmonic approximation to the sinusoidal modulation. This injection allows us to fully utilize the bus voltage. I'll leave a few links in the description that explain why that is, but let's go over a quick explanation. This is a sinusoidal modulation. These waveforms, which have a maximum amplitude of half the bus voltage, are the desired phase voltages. We know that what actually determines the phase currents is the voltage difference between the phases. Let's look at the voltage difference between two of the phases. We can see that the voltage difference between them doesn't quite reach the maximum limit, which is the bus voltage. It's short by around 15%. Ideally, we would simply increase the amplitude of the sine waves by 15% and reach the bus limit. But then the amplitude of the phase voltages themselves would exceed their absolute limit of half the bus voltage. So that's impossible. What to do? Well, someone, not sure who, came up with a really clever solution. Simply adding a single third harmonic to all three sine waves. This makes sure that the sine waves with the increased amplitude don't exceed their absolute limit, since the third harmonic subtracts from the peaks of the main sine waves. However, since there is only one harmonic, meaning it isn't phase shifted by 120 degrees between the phases or anything, the difference between the phase voltages cancels out the third harmonic, and only the main sine wave with the increased amplitude is taken into account. So this third harmonic allows us to increase our phase voltage amplitude by around 15%, and thus reach the voltage limit for the sinusoidal voltage differentials. The next step would be overmodulation, which would mean increasing the voltage commands past their saturation point, resulting in an increase in power output at the cost of some distortions. But that's a topic for another video. Here's how it's implemented in the code. So first we increase the amplitude of the signals by around 15%. Then, instead of adding a third harmonic, I add a third harmonic approximation, which is a triangular waveform at the same frequency as the third harmonic. This approximation is commonly used, since depending on the implementation, it can be more real-time efficient. Okay, next up, based on the desired phase voltages, we need to command the inverter, or essentially decide what the transistor values should be. And that way, we can approximate the phase voltages by using pulse width modulation. I'm using a center-aligned PWM signal here, so every tick of the MCU's clock, which is the simulation time step in our case, we're incrementally building a triangular waveform. and one triangle is a full PWM period. So we start by first figuring out where we are in the current PWM period. Let's say we're somewhere here. Next up, based on the desired voltage, we set the desired duty cycle, which translates to the compare value. So the maximum counter value will correspond to a duty cycle of 100%, and a 0 will correspond to a duty cycle of 0%, or vice versa, depending on the configurations. Let's say our desired compare value is here. Then we find where we are on the triangular waveform, according to where we are in the PWM period. Then we can set the top and bottom transistor values according to where we are on the waveform, compared to the compare value. The top transistor values are high when above the duty cycle value, and the bottom transistors are high when below the duty cycle values. I'm also adding a dead time to prevent the top and bottom transistor being on at the same time, and thus causing a short circuit. So when a switch in transistor state is required, the bottom transistors will turn off half a dead time period before the switch, and the top transistors will turn on half a dead time period after the switch. So there will be a total of one dead time period in which both transistors are off, meaning they're both not conducting. This dead time period causes some distortion, however, which we'll talk about soon. Let's see how it looks in the code. Find our time in the period, find the desired duty cycles, then find position along the triangular waveform, and then we set the transistor values according to that position, while taking the dead time into account. Let's go back to the main simulation function. Here's where we run the function to get the transistor values. I also added an option to simulate short circuiting of the phases by connecting them all to ground. We do this by setting the top transistors to low and the bottom transistors to high. Short circuiting is a common method used when a certain fault arises in the controller. For example, your position feedback experienced some issue, so you can simply short circuit the phases. This results in a braking force to stop the motor, with usually no need to operate any control loops. Now, based on the transistor values, we need to get the terminal voltages while considering the dead time distortion I talked about earlier. Since our motor phases are essentially inductors, when we enter the dead time period, all of a sudden, the currents don't have a transistor to flow through. And since an inductor's defining property is in opposition to a change in current, the voltage on the phases will change to oppose that change in current. Let's see what this means for positive and negative currents. Let's assume a positive current on one of the phases. In order for the current to continue flowing in the positive direction, it'll have to draw current from the bottom transistor, since that's the only path that allows for current flow through the MOSFET's body diode. In order for current to flow in that direction, the voltage on the phase must be slightly lower than the voltage at the bottom transistor. So we'll assume it equals the voltage of the lower transistor, which is the ground of the inverter. And if we assume a negative current, since the current must flow through the body diode of the top transistor, where the voltage is equal to V bus, the phase voltage will have to increase slightly over V bus in order for the current to keep flowing in the same direction. So again, we'll assume the phase voltage will equal the bus voltage. Here's an app note written by David Wilson, and we can see here that the phase voltage behavior isn't necessarily so clear-cut. However, as a first-order approximation, we'll assume the phase voltages are constant during the dead time period. Let's look at the implementation. In case both transistors are set to low, meaning we're in the dead time period, the phase voltages depend on the current directions and the bus voltage. Otherwise, the phase voltage depends on the transistor value and the bus voltage. Okay, now that we found the terminal voltages, what's left is to update a few parameters. We have the rotor angle, the self and mutual inductances and their time derivatives, the back EMF, and the torque. Let's start with the inductances. We'll assume a salient motor, meaning the inductance isn't constant and is a function of the rotor angle. We'll define an inductance in the Q-axis, LQ, and an inductance in the D-axis, LD. And the inductance will change as a function of the rotor angle, like so. All these angles are compared to an absolute zero angle, which is defined by the transforms used. In our case, the transforms were chosen so that when the angle is zero, Q-axis is aligned with the phase A. In the same manner, we'll find the mutual inductances. We see that the mutual inductances are negative, meaning the induced voltages on the adjacent phases will be negative. And finally, we calculate the self and mutual inductances time derivatives as well. Alright, now that we've finished with the inductances, we need to update the back EMF, since it's also position dependent. I'm assuming a sinusoidal back EMF with the possibility of adding harmonics to the waveform. Let's see what that would look like. Here is the back EMF with no harmonics. And here's the back EMF with the 5th, 7th, 11th, and 13th harmonics. Next, we update the torque generated by the motor. The torque equation is as follows. Right now, only synchronous motors are supported. Now, you might have these parameters from the motor's datasheet, which is great, but if you don't, there are ways to measure them. The flux linkage parameter is essentially the back EMF constant divided by 1.5 times the pole pairs. And the back EMF constant can be measured by rotating the motor at a certain speed while the motor isn't connected to the controller and measuring the peak voltage between two phases. The back EMF constant is that peak voltage per radians per second. Next up are the D and Q axis inductances. There are several methods to measure these parameters. Firstly, if you have an LCR meter, and assuming the cogging torque isn't too strong in the motor, you can measure the inductance between two phases at different rotor positions. The minimum inductance you measure divided by 2, since you're measuring across two phases, is LD, and the maximum inductance divided by 2 is LQ. If you don't have an LCR meter, or if the cogging torque is too strong, we can identify the inductances using the current response. We can use the controller itself to inject some signals in the D and Q axes to see the current response. We can, for example, inject voltage step commands and see the response, or inject the sinusoidal voltage command and see the amplitude and phase differences between the voltage and current measurements. And assuming we measure the phase resistance, we can calculate the inductances in both axes. And there are probably many other methods to identify the inductances. Going back to the code, here, all the parameters that might interest us are recorded. So once the simulation finishes, we can pretty much plot anything we want. One of the issues with running these kind of simulations is the very short simulation cycles. Right now, the default simulation cycle is 100 nanoseconds. This is done to be able to capture the dead time distortion accurately. So this simulation may take a very long time, depending on how accurate you want it to be. I assume there are also many improvements to be made, be it runtime related or otherwise. Let me know if anything obvious stands out. That's it for this video. I hope you enjoyed it and/or learned something. Have a good one. Till next time.